Okay, so hello everyone. Welcome to the MIT Vision and Graphics seminar. Today we are very happy to have Zachary Teed from Princeton University to join us. Zach is currently a fourth-year PhD, where he mainly focuses on 3D vision. In the past few years, Zach has done a lot of really amazing stuff in 3D, and I mean a lot. So he has done a lot of things, including optical flow, structural motion, scene flow, and I think the latest visual SLAM systems. And all of these work, they not only work, they work extremely well. So just to give you a sense, I believe a lot of you have heard of the optical flow network called RAFT. It was built by Zach, and it works extremely well. It sets multiple state-of-the-art records, and it also won the ECCV 2020 Best Paper Award for its contribution. And I believe there are a lot of intuition and secrets behind these designs. And I guess Zach is going to tell us all about these today. Yeah, Zach, feel free to take it.
Thanks so much for the introduction, and thanks for the invitation to speak at the seminar. So I'd like to talk about our work on optimization-inspired neural networks for multiview 3D. And I want to start by showing the types of systems that I'm trying to build. So what I'm really working towards is dense 3D perception. We have a camera moving through an environment, and what we really want is a dense reconstruction of the environment. Additionally, I want to show how this camera moves through such a scene. And ultimately, what we want to say is every voxel in space, whether it's occupied or not. And I think a really interesting application of this is towards dynamic scenes. So instead of assuming the scene is static, we can now have moving objects in the scene. And assuming only the raw images as input, I would like to reconstruct reconstructions such as that shown to the right, where we have a dense reconstruction of the static background, and we can show how dynamic objects move through the scene. And this is a very hard problem because when we only have raw images as input, there's a lot of unknowns. We don't know the trajectory of the camera. We don't know the intrinsics, or if there's distortion. Depth and 3D motion are all unknowns. So this type of technology has a lot of important applications, particularly in robotics. Anytime we have a robot interacting with the real world, we need to 3D model that world. That includes both the static scene and then also the dynamic objects, so that we can perform path planning, collision avoidance, and these types of systems can perform safely. 3D scanning is another really important application that I'm excited about. Ideally, we would like to be able to take a video or a set of pictures of some object and essentially create a digital twin of that object, such that we can import it into graphics, animations, or computer games. It can also be used for inspection, such as infrastructure inspection or those types of applications. Finally, this type of technology is really important for augmented and virtual reality. So for these types of applications that have a good user experience, we need accurate camera pose estimation. And then we also need a reconstruction of the scene around the object in order to kind of overlay these digital objects in the real world. So these types of problems have traditionally been approached using continuous optimization. And what the optimization problem sets up is we have an optimization variable. And in these cases, we're trying to estimate flow, depth, disparity, camera pose. And this is conditioned on the input data, such as an image, video, or stereo frames, for example. So what we first do is we build an objective function. And this objective function tells us a measure of how good a particular solution is. Once we have the objective function, then we need to create a search algorithm for finding a solution which minimizes the objective. And in the case of continuous optimization, the search algorithm is usually performed by maintaining a single estimate of the variable we're trying to optimize over. And then with each iteration, we propose some increment. And this can kind of be visualized using this figure where this optimizer performs an update to the variable at every optimization step. And usually this optimizer will have some idea of a hidden state, such as primal dual variables or trust region, for example. But it's basically important that this optimizer has some history of the variable it's trying to optimize over. And this is a really effective strategy for multiview 3D. Because it allows us to explicitly model geometric constraints. For example, if we have a 3D point, we know how the 3D point gets projected onto each of the images, and we can model this using like reprojection error, these types of loss functions. Then during inference, we search for a solution which maximally satisfies these geometric constraints. And this type of problem shows up in many, many different multi-view 3D applications. For example, like multi-view stereo, pose graph optimization, 6D object pose, like even camera calibration. When we're trying to model these more complicated camera models, we usually need to rely on some sort of continuous optimization. And then of course, structure for motion, where we're trying to optimize for 3D points and then the camera poses jointly. But there's a lot of limitations of this approach when we're trying to apply it to like real world data. For example, designing the objective is not always trivial. In the case of structure for motion, it's pretty easy to say we want 3D points to map onto the image, but we need this objective to be robust to outliers. Lots of times we want to impose some sort of prior in order to make the problem actually solvable. And in many cases, like multi-view stereo, it's actually very difficult to even come up with an objective function which tells you a measure of how good your solution is. Additionally, it's really hard to optimize these problems, especially for 3D vision tasks. These types of optimization problems are very difficult to converge to a global minimum because camera poses lie on a manifold. There's usually a lot of outliers. And typically what you find is that the more work you put into designing this good optimization objective and imposing stronger priors, the more and more difficult it becomes to actually solve these optimization problems. So deep learning is a completely different solution to a lot of different vision problems, and it's had a ton of success on semantic tasks such as object detection, pose estimation, and segmentation. And it takes a radically different approach than these optimization-based schemes. So essentially what deep learning is you take an image as input and then you map it into a set of outputs. So a natural question is like, why not just directly apply deep learning to estimate 3D properties? And this has been done with a good deal of success. And maybe one of the most successful applications of this is deep learning for depth prediction. And for depth prediction, we can take a deep neural network and we can train it to estimate depth from an image or video. So if we take the DPT, which is the latest transformer-based depth estimation network, which is trained on a combination of 10 different data sets, we can get this kind of result. And this looks fairly good. However, when we actually visualize the point cloud in 3D space, we start to notice that there's quite a bit of artifacts and that this type of reconstruction is not obeying geometric constraints. Compared to the ground truth, it's kind of difficult to tell exactly what's happening in the scene. And the problem is a little bit more apparent if you look at geometrically more complicated scenes. Like this example from Sintel has this bamboo, which really makes this a very difficult scene to reconstruct using just deep learning. And looking at the reconstruction, it's very difficult to tell what's happening. So deep learning has also been applied to multi-view problems. And some of the early work for applying deep learning to multi-view problems typically take generic neural network components and formulate these problems as image-image mapping. So in the case of FlowNet, we can take two images and directly try to predict optical flow. Deep visual odometry, what they do is they take a sequence of video frames as input and then estimate the relative camera poses between a sequence of frames. And similarly, Daemon looked at trying to estimate depth from a pair of images. And these approaches have a number of different advantages. Usually they are very fast compared to the classical optimization-based counter approaches. But in general, it's not quite as clear cut whether they're actually outperforming these classical systems. Additionally, there's some other issues, like they're often very difficult to train. And what we really want is systems that can generalize. So if we train it on one data set and apply it to a new data set, ideally it should work on that new data set. But for many of these early deep networks for these types of problems, we don't get great generalization. So the strategy that I'm going to talk about is trying to design neural networks to behave like optimization algorithms. So this is an idea that has shown up in many works in the past, especially in the case of modeling inverse problems. So we can take this optimization algorithm and kind of compose it as a computation graph. And then we can replace each individual like hard-coded algorithm with like a learned neural network component. And this has a number of different advantages, which I'll discuss in this talk. So we rely on two key ideas. The first is iterative updates. And what these iterative updates aim to do is they aim to learn a data-driven search algorithm. So each of these updates will take in the current estimate of the variable we're trying to optimize and produce an updated estimate. We additionally rely a lot on implicit layers. And what we use these implicit layers to do is impose geometric constraints during inference. These will usually take the form of these mini optimization problems, which we solve during the forward pass of the network, and then backpropagate through these mini optimization problems during training. And these can be used to impose a geometric constraint, such as the mapping of a 3D point onto the image. And the approach we take is to give a neural network direct control over these types of implicit layers. So we have a neural network and we have these implicit layers. And what we use is we take these neural networks and allow them to shape the optimization landscape of these. And this can be used by like adjusting the weights of least squares optimization layer. But then we take the solution and feed it back into the neural network. And we perform this loop many times during inference. So the neural network can actually take the output of these optimization layers and then adjust the input and then observe the output and make changes. So we've applied this type of idea to many different important vision problems. So this talk is focused on 3D reconstruction. Optical flow is not necessarily a 3D task, but it provides a like very important foundation for many of these more complicated 3D applications. So we've also looked at 2D stereo, scene flow, which is the 3-dimensional analog of optical flow, and then SLAM and structure for motion. We've additionally developed some tools that allow us to more efficiently perform backpropagation through computation graphs consisting of Lie groups, which show up a lot in these 3D vision applications. So our work on optical flow, while this is still a 2D task, served as a building block for our work on stereo, scene flow, and SLAM. Additionally, we've used these tools that we developed on these tasks such as scene flow and SLAM, where we're performing inference over 3D transformation groups. So in this talk, I'm going to look at 3 particular projects which should help to kind of illustrate these ideas that we apply. So I'm going to start by talking about our work on optical flow. So optical flow is a fairly simple problem, and it has a long history in computer vision. We're taking 2 images input. So in this image, you can see that there's some motion between these 2 images. And what we want to output is a dense pixel-wise 2D motion field between the pair of frames. This can be visualized as a vector field shown in this image, but we can also visualize as a RGB image where we map the direction and magnitude of each optical flow vector as an RGB channel. So optical flow has been traditionally approached as an optimization problem. And the objective balances an appearance constancy term and a regularization term. What this appearance constancy term says is that it wants us to match visually similar image patches. But this typically isn't enough information to solve for optical flow. So in order to combat some of these ambiguities, we additionally impose a regularization term. And this regularization term typically comes in the form of a piecewise smooth motion prior. So we know that similar pixels, nearby pixels should have similar motions, with the exception if they cross a motion boundary. And there's been a lot of work on optical flow. So various works have explored trying to create better visual similarity metrics. Other works have explored more robust regularization terms. And many of these works have also explored more efficient algorithms to actually solve for motion fields given this objective function. So deep learning is another approach to optical flow. And deep learning really sidestepped this optimization formulation. And FlowNet showed that you could directly predict optical flow between a pair of frames. Some of the more recent architectures like PWCnet or SpyNet imposed more of these classical data structures within the optical flow estimation framework. So they use ideas like image warping and cost volumes and iterative refinement to impose some inductive biases in the network. And there's been a lot of work on using deep learning for optical flow. And with some exceptions, most of these works kind of take the form of this coarse-defined framework that was popularized by PwCnet and SpyNet, where they estimate large displacement optical flow at a coarse resolution and then upsample and refine small displacements at a higher resolution. So our work RAFT was a new type of neural network architecture for optical flow. And RAFT stands for Recurrent All Pairs Field Transforms. So what we want is we're taking two images as input and we want to produce this flow field. And as I mentioned before, in this optimization formulation, we want to create some measure of visual similarity. So we do really the simplest thing possible is we extract features from the input images, and then we simply take the correlation between every pair of feature vectors. And you can think of this as a 4D correlation volume, such that we have for every pixel in the first image, it's correlation with every pixel in the second image. One minor detail is that we're actually extracting these features at 1/8 resolution. So this correlation volume is not built in the original image space, but at a slightly downsampled 1/8 resolution. And this allows us to not really require a ton of GPU memory so that this can be efficiently trained and run at inference. We additionally extract context features from the first image, and then we iteratively refine a fixed resolution flow field by performing lookups from this correlation volume and producing optical flow refinements. And what each of these update operators does is it takes in the current estimate of optical flow, it performs lookups from this correlation volume, and then produces a new estimate of optical flow. And these iterative updates are performed at 1/8 resolution. So there's no coarse-defined pyramid. This whole network is operating at a fixed resolution. So I'm going to talk about these components in a little bit more detail. So to start with the all pairs correlation volume, what we do is in the feature vector space, we take the correlation of every pixel in the first image with every pixel in the right image. And looking at this pixel in green, we can visualize its two-dimensional slice in this 4D correlation volume. And you can see that we end up getting some maximum values, and these kind of correspond to areas that have high visual similarity. We then perform repeated average pooling over the last two dimensions of this correlation volume. And again, I'm visualizing this 2D slice corresponding to the green pixel. And what this average pooling does is it kind of smears out these high confidence activations. Finally, we define a lookup operator, which we use to retrieve features from the correlation volume. So let's say we have a current estimate of optical flow shown in the red pixel. So what we do is we construct like a 9x9 neighborhood grid. And we use this 9x9 grid to sample from each level in this correlation pyramid. So when we index from the high resolution pyramid, this gives us information about small displacements or displacements in a very local window of our current estimate. But when we sample from these coarser resolutions, it gives us information about coarse information. So it allows us to make large corrections to the optical flow field. And as our optical flow field gets more and more accurate, then ideally we should be sampling around the correct optical flow. So the first level of the pyramid will give us this fine-grained information that we need to correct. This update operator is a GRU-based update operator, and we use a GRU because it allows us to maintain a history of past flow estimates. So this GRU actually can encode the history of optical flow estimates that we've received per pixel. And what this convolutional GRU does is it uses, at every iteration, it uses the current estimate of optical flow to perform this lookup operation I just described from the correlation volume. And what this is designed to do is this convolutional GRU is designed to mimic the updates of a first order optimization algorithm. But we define no explicit objective or gradient. Instead, we use the correlation features to propose the update direction. Since we're estimating optical flow at entirely a fixed resolution, supervision is super easy. All we need to do is we just apply a loss function to each intermediate flow output. We use a weighting scheme such that the later iterations receive more weight than the earlier iterations. But we simply just take the L1 distance between the ground truth and the predicted flow. Since we need ground truth optical flow, and this is typically very difficult to obtain in practice, we train primarily on synthetic data. So we follow the standard flying chairs to flying things training schedule that was proposed in the FlowNet 2 paper, but we reduced the total number of training iterations from 1.7 million down to 200,000. So this is much faster to train than some of these prior flow networks. Additionally, after the synthetic training, we can perform data set specific fine tuning either on the Sintel data set or the KITTI data set, for example. So I'm going to talk about some of the results that our network's able to get. So first of all, I'm looking at this generalization result. So when we train on chairs and flying things, what are our results on the Sintel data set? So here I'm showing the results in both the clean pass and the final pass. And it's important to know that this network has never seen any Sintel data. It's only seen these other synthetic data sets. So we typically will see about like a 30% improvement over the prior work in this generalization setting. And we also see similar results on the KITTI data set where we're seeing about a 30% better generalization than prior work. Here are the results on the Sintel benchmark. These are from around ECCV when we submitted this network to the Sintel benchmark. And we see similar results, about a 30 to 40% improvement over prior work on both the clean pass and the final pass. And I'm going to show some qualitative results as well. So here are some visualizations of the flow field compared to PWCnet, and kind of what's important to look at is like our network's able to recover a very high degree of detail, especially like in the top figure, you can see that it's able to estimate the optical flow of these small, fast-moving birds. Here is a comparison to volumetric correspondence network, and then the more recent mass flow net which was kind of built on PWCnet. And all these networks I just showed, they adopt this course-defined processing framework where we show that we can actually estimate accurate optical flow without any of this course-defined processing. Here's some visualizations of the flow field when applied to video. I think these are just interesting to look at just because I think it's important to show that there's actually some temporal consistency in the flow field. And then this is the example of the video on the test set where there's the birds. So I've argued that RAFT is mimicking the updates of an optimization algorithm, and I want to demonstrate that empirically this does turn out to be the case. So if we look at convergence as a function of the number of iterations, we can see that later iterations produced better flow fields than earlier iterations. And this was particularly noticeable in these thin structures, which are typically missed during the very early iterations, but are recovered later on. Here is the endpoint error, which is the metric we're primarily using on Sintel as a function of the number of iterations. And I'm showing endpoint error both on the clean pass and also on the final pass. And again, what we see is that this endpoint error decreases as a function of the number of iterations. Our network is trained by enrolling 12 iterations, so we're kind of seeing after about 10 or 12 iterations, the performance tends to saturate, but there is actually some additional benefit towards using more iterations. And this is particularly apparent if you're looking at like the very thin structures, which the thin structures don't contribute a lot to the final error value, but just because they consist of very few pixels. But it is, I think, generally important that these types of structures are recovered if we're trying to do any type of downstream task. Here are some additional results on the KITTI dataset, in addition to the qualitative results. And this is what the results we get when we benchmark our optical flow network on the KITTI dataset after training on the training set. So you may be wondering, given the quadratic complexity of this all pairs correlation volume, like how well does this actually work on high resolution images? So we apply our network on the Davis dataset at 1080p resolution, so megapixel images. And it turns out that the correlation volume really only takes about 20% of computation time, even at these very, very high resolution. The problem you do start to run into, though, is that even though it's not a computational bottleneck, storing the correlation features for this full volume takes up a lot of GPU memory. In our paper, we showed that there's a low memory implementation that actually avoids storing the full correlation volume. So when you're operating at even higher than 1080p, that's could be particularly useful. Here's some additional video results on the Davis dataset showing the soccer ball and the camel scene. And again, the network I'm showing here is trained entirely on synthetic data, and we're able to see good qualitative flow results on this real data that it hasn't seen before. So since publishing this paper at ECCV, there's been a number of applications I think that are exciting. And in many of these applications, these papers showed that taking a better optical flow network actually ended up getting better results on these downstream tasks. So some, I think, exciting applications are like what I discussed earlier is like trying to reconstruct these dynamic scenes. If we can compute optical flow between pairs of frames, this gives us an important signal that we can use to guarantee the consistency of these dynamic reconstructions. There's also been some work on video object segmentation and video panoptic segmentation, which use RAFT as input. I thought one interesting application is video object segmentation using RAFT. And this ICCV paper showed that you can actually use RAFT to detect like camouflaged animals. So given these RGB images, it's really very hard to detect where the animal is, but if you actually look at the flow field, it's much easier to perform detection. So I thought this was one interesting application. As I mentioned before, I'm primarily focused on 3D vision, but RAFT only looks at 2D optical flow. One very simple extension to make RAFT 3D is looking at the problem of stereo matching. And stereo matching is kind of just the one-dimensional analog of optical flow. With optical flow, you can really match any pixel in the first frame to any pixel in the second frame. With stereo matching, we have a constraint that every pixel in the left image lies on a horizontal line spanning the second image. So really the only change we needed to make to RAFT was we just needed to construct a 3D correlation volume instead of this 4D correlation volume. We additionally looked at using like multi-level GRUs, and these helped us to better propagate spatial information across the image. But overall, simply replacing the 4D correlation volume with the 3D correlation volume made the biggest difference. So this recent paper, it ranks first on the Middlebury stereo benchmark. So you can see that compared to some of these prior deep learning methods, we were able to reconstruct a very high level of detail, like the spokes on the bike or these individual leaves on the plants. So if you look at the 1 pixel error on the Middlebury stereo benchmark, we get a 1 pixel error of 9.3% compared to the previous best of 13%. But I think it's also important to look at like how do these reconstructions actually look if you back project it into 3D. So here are some additional examples from the Middlebury data set. So you can see that there's still some error, like it's certainly not perfect. There's some missing regions, there's some flying pixels, but overall we were very happy with the quality of these point clouds that we were able to produce. And here's an example from the bike scene where we're able to reconstruct even the spokes of the bike in many cases. And this is one final example where there's almost no texture on this table or the wall behind it, but we're still able to get good reconstructions even in these very limited texture areas. Okay, so the next part of my talk is I'm going to focus on our work on Visual-SLAM. So in Visual-SLAM, SLAM stands for Simultaneous Localization and Mapping. We're given a video as input, and this can be a monocular video, a stereo video, or an RGB-D video. And what we want to produce is a 3D map of the environment and the trajectory of the camera as it moves through the map. And this is essentially what I showed before. Like, we want to produce systems like this. We want dense, accurate reconstructions and also the trajectory of the camera. Most typically in Visual-SLAM, the performance of the system is evaluated based on the accuracy of this trajectory that we estimate. And the only way to get a good camera trajectory is to also have a good model of the environment. So classical Visual-SLAM formulated the problem as an optimization problem. And these can be divided into two different categories. The first is indirect SLAM. And what indirect SLAM does is it first detects key points in the images, and then it matches key points. And then it minimizes the geometric error between the observed 2D key point motion and the induced 2D key point by the solution. So so we first detect key points, and then we minimize the geometric reprojection error. And this is similar to what's being done in most structure for motion systems. Direct SLAM takes a different approach, and it actually directly models the image formation process. So instead of minimizing this geometric reprojection error, it minimizes a photometric error. And this is typically computed by like warping pixels from one frame onto the other, and then computing the difference between raw pixels intensity. And some examples of direct SLAM systems are LSD SLAM and then direct sparse odometry. And these systems have been producing really good results. And when they work, they typically work very well. The problem with these classical SLAM systems is insufficient robustness. Failures are frequent, and when they fail, the results are usually catastrophic. So there's kind of this binary, they have this binary performance, whether if they work very well. If they don't work, they give results that are not usable. Additionally, there's been a lot of work on trying to apply deep learning to visual SLAM. And many of these systems attempt to estimate pose and depth directly from a pair of input images. The problem with deep visual SLAM, though, is it has much lower accuracy than the classical counterparts. And also, it typically suffers from poor generalization. Often, it won't generalize outside of the data sets it's trained on. So here are some results from the EURIC dataset, which is commonly used to benchmark classical SLAM systems. And I took a couple recent deep learning approaches and showed the results compared to ORB SLAM. And what you see here is that these deep SLAM systems are typically performing 10 or 100 times worse than the best classical SLAM systems. So there's really a huge difference in accuracy between what you get with the deep SLAM systems and the classical SLAM systems. What we would propose is a new system, a new SLAM system built using deep learning. And we call the system DROID-SLAM. DROID stands for Differential Recurrent Optimization Inspired Design. And what we really focus on is closing this accuracy gap between these deep learning systems and these classical systems. We also put a lot of emphasis on robustness. We really want the system to work like anytime we use it. Like you can just take a video with your cell phone and it should produce good reconstructions. And finally, we're trying to build a system that's actually generalizable. It's very unlikely that the system is going to be applied to the same data it's trained on. So we want a system that will work on new data that it hasn't seen before. So to kind of motivate our design, I'm going to start with the fact that optical flow is an analytical function of depth and camera poses. And I'm going to show just a brief background of this, like this functional form. So if we have a 2D point in image 1, we know its inverse depth, we can compute its 3D coordinate. We can compute its 3D coordinate by back projecting this 2D point. We can then transform this 3D point from the coordinate system of image 1 into the coordinate system of image 2, and then just simply project this point onto camera 2. And we can compute something we call an induced flow, which is the difference between this projected point and the difference between the original point. And this is identical to the optical flow that you get if you were to estimate optical flow between these two images up to the prediction error. And this inverse projection, transformation projection, I'm going to use so commonly that I'm just going to define the notation omega, which takes every pixel in frame I and computes its projected location in frame J. So basically, given any pixel in image I, if we know its depth, we can find its location in image 2. So given depth and given camera pose, we know how to compute optical flow. But what about going in the reverse direction? So given optical flow, can we compute pose and can we compute depth? And this is a very classical problem, and it's typically solved using bundle adjustment. So what we want is we're using optical flow. We have optical flow between frames I and frames J, and we want to recover the depth and pose. So let's say we're given a co-visibility graph, And we have some algorithm for computing optical flow between edges in this graph, so frames that have visual overlaps. And we want to estimate depth, and we want to estimate camera poses. So what we can do is we can formulate an optimization problem. We can take the sum over every edge in this frame graph, and we can take the difference between this predicted flow as predicted by our flow network and the induced flow, which is a function of depth and pose. By minimizing this objective function, we can solve for depth and we can solve for camera poses. This is a nonlinear least squares problem, and there's iterative algorithms like Gauss-Newton and LM, which work typically pretty well. So this motivates kind of a naive SLAM system. What if we just apply RAFT, estimate flow between pairs of frames, and then just use an off-the-shelf least square solver to solve for camera poses and depth? This turns out to work actually very poorly, unfortunately. And this is because of outliers. RAFT doesn't tell us whether or not a point becomes invisible in the next frame. There's dynamic object, and there's also prediction error. So how do we exclude outliers and make this more robust? First of all, we can also have RAFT predict a confidence map. So we can ask RAFT to say how confident it is with a particular correspondence. The other idea is apply feedback. So once we have the solution to this least squares optimization problem, we can feed it back and plug it back into RAFT. So this motivates a new idea. What if we integrate RAFT directly with dense bundle adjustment iterations? And this goes back to the figure I showed earlier, where we can have this GRU shape this optimization landscape and then have the solution fed back into this network. So this is what our DROID-SLAM architecture looks like. DROID-SLAM performs iterative optimization over all depths and camera poses. And it does this using analytically constrained updates. So just like RAFT, we start by extracting features from each input image and then build a correlation volume. However, instead of operating on a pair of images, we're actually operating on a video consisting of maybe even 1,000 images. So yeah, first we extract features and build a correlation volume, and we build a correlation volume between each edge in this visibility graph. We will then perform a set of iterative updates, and each of these updates produces an update to all the camera poses and all the dense depth maps jointly. So what does this look like? First of all, we use the current estimate of camera poses and the current estimates of depth to use this omega function to compute the correspondence between each edge in the frame graph to compute the induced flow. And this is performed over all edges in the frame graph. We then use these predicted correspondences to index from the correlation volumes. And these correlation features alongside the flow features are plugged into the convolutional GRU. What this convolutional GRU produces is it produces an updated hidden state, it produces a flow revision, and it also produces a confident estimate. And these are plugged into this dense bundle adjustment layer, which I'm going to describe now. So using this warping omega function, we can compute the correspondence estimate using our current estimate of poses and depths. We update this using the revision as predicted by the network. And then we model a least squares optimization problem. And this optimization objective sums over every edge in the frame graph, and it takes the difference between this induced flow and then the predicted flow. Additionally, we use this predicted confidence to weight the optimization problem. And again, and this is typically what we find when we visualize the confidence prediction. So the X confidence will often correspond to vertical lines, whereas the Y confidence will often correspond to horizontal lines. And again, this is a least squares optimization problem. We can linearize it and we can solve it. So what we do in practice is we unroll 2 or 3 updates, 2 or 3 linearization solving updates of this dense bundle adjustment layer, and then we differentiate through each individual update. This allows us to backpropagate the gradient through this optimization layer. And what that allows us to do, allows us to train this confidence estimate, even though we apply no direct supervision to this confidence itself. We supervise our network on a pose loss, which gives the difference between the ground truth and the predicted flow, and also a flow loss, which takes the difference between this induced flow and the ground truth flow. And this is trained entirely on synthetic data. So during training, we train our network on sequences of about 7 frames as input. But during inference, we really need to apply this on video of arbitrary length. Like it could consist of video of 1,000 frames or even more. We perform inference using a double window optimization scheme. So we have a front end, which is optimizing poses and depths in a local window. So as each incoming frame is added, we're performing optimization over like the recent set of like 7 or more frames. And this front end is also performing things like keyframing and other SLAM system stuff like that. This back end is optimizing over the poses and depths of the entire video jointly. And this back end, it's able to actually perform loop closure because if we revisit an already mapped area, we can create this long range connections in this frame graph and estimate optical flow between frames that are spatially close but temporarily very distant. And there's a simple extension of this algorithm to stereo and RGB-D frames. For stereo, we simply double the number of frames in the graph, and we can simply fix the relative pose between the left and the right frame. For RGB-D, we still estimate depth. So depth is still a variable in our optimization problem, but we use sensor depth as a prior in the dense bundle adjustment layer. So all we have to do is just add an additional term saying that we want our predicted depth to be close to the sensor depth in regions where the sensor depth gives us a measurement. And the reason why depth is still considered a variable in this optimization problem is that sensor depth can have noise or missing observations. So when sensor depth is missing, we still want to estimate the depth of variables, even though we have no depth measurement. And kind of one of the cool things about the system is that this is the extension to stereo or RGB-D only happens at inference time. We train our network entirely on monocular data, and no retraining is required for stereo or RGB-D. So our network is trained entirely on the Tartan-Ayer synthetic data set, and I'm showing some examples of what this data set looks like to the right. And we benchmark our system on the ECCV Tartan-Ayer SLAM challenge. So I'm comparing to the top 3 submissions to the ECCV 2020 SLAM competition. And so in this particular setting, we're seeing a 62% reduction on the monocular setting and a 60% reduction in the stereo setting. Additionally, here are some results of the trajectory that are estimated by our system. So in the case, if the trajectory has any sort of loops, we typically find that since we can perform loop closure, we can really get near zero drift in these loopy trajectories. The trajectory that performs the worst is this MH005, where you can see that there's no loop in this trajectory, and there's some drift that accumulates over the course of the video. But the amount of drift here is still fairly low. Also, we can look at, so these are results from a validation split I made of the data set, and we can look at the results compared to whether or not we use stereo information. So I'm showing results of the monocular system in black and results of the stereo system in blue. So we typically see much better results when we're using stereo because this gives us more information. It corrects any issue with scale drift. And even though we don't train on stereo data, we do get a pretty large benefit when we use stereo data. Additionally, I'm showing, so the bold lines here are showing the results of the full system, whereas the dotted lines are showing the system where I'm only using the local front end. So the bold lines are also using this back end, which is performing loop closure. So what we're also seeing here is that when this back end is used that's performing global optimization and loop closure, we're also getting much better results. And this is particularly apparent if you look at the absolute trajectory error around the 0.1 meter range. There's a huge improvement when we're using this global optimization. We also benchmark our system on a variety of real-world data sets. So here are the results on the EURIC MAV dataset, where I showed the performance of deep SLAM systems prior, and these prior deep SLAM systems were performing 10 or 100 times worse than ORB-SLAM 3. Here I'm showing results of our system compared to ORB-SLAM 3. And we actually outperformed these classical SLAM systems on 10 of the 11 sequences. And our system is trained entirely on the Tarn-Air data set, so it's never seen real data before. So we get fairly good generalization from the synthetic to real. We also benchmark on the TUM RGB-D dataset, where even though the TUM RGB-D has depth information, we're just using it to benchmark the monocular performance of our system. On this dataset, it's particularly difficult because there's a lot of motion blur, there's roll and shutter artifacts. So we find that these classical SLAM systems, such as ORB-SLAM 3, tend to fail on a large percentage of these videos. Our system is able to track all the videos, and it ends up getting an 80% reduction in error compared to some of these previous deep learning systems, like deep factors, for example. We finally also submit to the ETH3D SLAM benchmark, and ETH3D is an RGB-D benchmark, so we're actually using the depth stream in this example. And our system ranks first on this benchmark, and it's able to successfully track 30 of the 32 RGB-D sequences. So we only fail on about 7% of the images, whereas the next best method only tracks 21 of the 32. So this is kind of feeds back into our claim that this is a much more robust system. The failure cases are much rarer. So here are some results that our system is able to produce. All these results I'm going to show are done in the monocular setting, where we're only given images as input. Here's a result from the Tanks and Temples data set. And here's some additional results on the ETH3D benchmark. The blue trajectory shows the location of the camera pose as it moves through time, and then we're also back projecting the 3D point cloud, the depth estimates to a 3D point cloud. This is what our system looks like when we apply it to a scene from the Tanks and Temples benchmark. So this can operate in real time. In the case of the Tanks and Temples dataset, it's actually operates about 2 times faster than real time because the camera motion is fairly slow. And what you can generally see is it performs multiple loops around this building, but there's no really inconsistencies. It's able to perform loop closures, so we get a globally consistent reconstruction. I also took some video with my phone around the Princeton campus. And so these are the types of results that you can expect with just a real-time SLAM system. I think there's definitely room for a lot of improvement in terms of the quality of the reconstruction, but I was pretty excited to get this density, this type of dense reconstruction in real time. And then I'm just going to show one kind of more complicated example. And this is another video I took with my phone. As I am kind of doing this exploratory trajectory around Princeton. Yeah, and then so in this projector, it's gonna loop back to the original location, and you can see that there's a bit of error that accumulated through this trajectory. So it seems about a couple feet of error. And this is a large part of this error is due to the fact that most phone cameras have a roll and shutter camera, at least in this case. So there's some geometric artifacts that accumulate, causing some of this error. But it's actually possible to perhaps model these roll and shutter artifacts to improve the trajectory over these using kind of more common cameras. So our work on SLAM assumed a constant scene, but what if there are moving objects in the scene? So in scene flow, it's considered to be like the 3-dimensional analog of optical flow. We take a pair of RGB-D or stereo frames as input, and these frames come from a dynamic scene. And what we want to output is a dense per pixel 3D motion field. So what this diagram is showing is that our scene flow, or like the motion of pixels in 3D space, projects down to optical flow. So given optical flow, we want to recover this 3D motion. And there's a couple of naive solutions that we can consider for this problem. Like we can take 2 images as input, we can directly apply RAFT, and then we can ask RAFT to maybe predict 3D motion instead of 2D motion, or we could ask it to predict other parameterizations of 3D motion, such as optical flow, and then back project the pixels or optical flow, and we can ask it to estimate depth change. We found that these typically work okay, but we'd like to do a lot better. So in the problem of scene flow, many scenes can be described as a collection of rigidly moving objects. So if we look at this input sequence here and we look at the optical flow, there's not a lot of structure to this flow field. But if we look at the rotation and translation components of a 3D rigid motion field, there's actually a lot more structure. If the scene consists of only rigidly moving objects, this optical flow field is going to be piecewise smooth, while this rotation translation field is going to be piecewise constant. So instead of in the case of DROID-SLAM, we were estimating an SE3 transformation per frame. In the case of scene flow, we now want to estimate an SE3 transformation per pixel. So we want to recover these dense transformation fields shown to the right. And we can make a fairly simple modification of our DROID-SLAM architecture to estimate dense 3D transformation fields. So instead of performing iterative updates to camera poses, we're now going to perform iterative updates to dense SE3 fields. So we have a per pixel transformation that we want to update using an iterative architecture. So the main update we make here is that in addition to predicting this hidden state, revisions, and confidence, we also want to predict per pixel embeddings. And the idea of these per pixel embeddings is to softly group pixels into rigidly moving objects, such that the likelihood that 2 pixels belong to the same rigidly moving object can be computed based on the difference between their vector embeddings. And a question we want to answer is, can we learn to group these moving objects without any segmentation supervision? So what we do using these embeddings is we use these embeddings to build an attention matrix between all pairs of pixels. So we can build this 4D volume, which tells us the likelihood that all pairs of pixels belong to the same rigidly moving object. And we use this sigmoid, we use a sigmoid function to map this to a 0 to 1 score, which tells us the likelihood that 2 pixels belong to the same rigidly moving object. We use the exact same objective function. We use the exact same optimization function that we're using in DROID-SLAM, where we're using this GRU to predict a revision, which is applied to the current estimate of correspondence. The difference now is that we're weighting this optimization objective based on this attention matrix. And so what this optimization problem is saying is that for this pixel shown in the green, we want it to describe all pixels, the motion of all pixels in a neighborhood around that green dot. So if for all the pixels that share a similar embedding, we want this single transformation at this point to describe the motion of its neighborhood. And we perform optimization over the full image, so we perform optimization over all the transformations over this full image. Again, this leads to a very large optimization problem it can have. So we linearize and solve this, but it can lead to a very large optimization problem with 50 million residuals. But kind of the key thing is that we can actually break this up into much smaller optimization problems and solve each one individually. This still is very computationally intensive, but using an optimized CUDA kernel, we can actually solve for a dense 3D transformation field, given these embeddings, given these updates and these confidences predicted by this GRU. Again, we differentiate through this optimization layer, and that allows us to backpropagate. And even though we provide no direct supervision on these embedding vectors, by differentiating through this optimization objective, we can actually train these embedding vectors without direct supervision. So here I'm looking at the results compared to some previous 3D networks for estimating scene flow. And many of these prior networks operate in the 3D space, so they're actually trying to predict 3D motion using point clouds as input. So maybe a better comparison is to some of our RAFT baselines. So we look at our RAFT where we predict 2D optical flow and then back project the 2D motion vectors. We also experiment with variants where we directly predict 3D flow, or we predict 2D flow plus depth change. All these formulations are sufficient to parameterize 3D motion. And what we find is that, particularly in this strict 3D metric, we're able to do much better when we reason about in the space of 3D transformation fields as opposed to 2D motion. And this allows us, and the reason for this is that this 3D transformation field, since it's piecewise constant, is a much more structured representation to reason over, as opposed to optical flow, which is piecewise smooth. We also benchmark this approach on the KITTI scene flow benchmark, and at the time of submission, this outperformed all published work on the KITTI scene flow benchmark. And what was kind of exciting about this is that we use no instance level supervision. So this was trained entirely on optical flow, yet it was able, as I'll show, it was actually able to learn to group objects into rigidly moving clusters. So here are some qualitative results showing that our system is actually able, even without any direct supervision, is actually able to learn to segment the scene into a collection of rigidly moving objects. So here in image one, I'm showing the image one, I'm showing the optical flow, which, as I mentioned before, it's smooth, but there's not a lot of structure to this. But if we look at the rotation and translation components of the 3D motion field that our system's able to estimate, these are actually piecewise constant. So, and then looking at the KITTI images below, we see a similar thing where the network is actually able to segment the scene into rigidly moving objects, even though it has no direct instance level supervision. So in conclusion, I've been working on optimization-inspired neural networks. And the main goal is to design neural networks which behave more like optimization algorithms. And this allows us to achieve kind of the accuracy that you'd expect from these classical optimization algorithms, while being like much more robust in these real-world settings. And one of the main ideas I looked at is this tight integration of neural updates with implicit layers, where a neural network can shape the optimization landscape of these implicit layers and then receive feedback from the output of this optimization layer. We've applied this idea to a lot of important vision tasks, including optical flow, stereo, and visual SLAM. And this has really provided us with like a general framework for constructing neural networks for a large variety of important vision problems. So I'd be happy to answer any questions if anyone has any questions.
I think we are running out of time, so maybe we can take one question. Did anyone have any question? Okay, then I'll ask a really quick question. So during your SLAM work, I think you said you optimize like, you have lots of depth images, right? And you try to optimize that. And what happens if 2 points, like 2 different pixels, they are corresponding to the same 3D points? Do you enforce any consistency on their depth so that they are...
yeah, no, yeah, that's a good question. We don't enforce any consistency between the pixels. So I think that's, especially in the case of dynamic scenes where you, like if you're trying to reconstruct dynamic scenes, it really becomes important to enforce this consistency. The problem in the case of visual SLAM is if you add these constraints between different pixels, then it actually modifies the structure of the linear system you're trying to solve, and you can no longer efficiently solve it using the Schur complement. So I think it would be nice to enforce that kind of constraint that corresponding pixels map to the same 3D point, but it makes the optimization problem like infeasible to solve in real time.
I see. Okay, thank you. So, okay, I guess that's it. And yeah, thanks, Zach, for your talk again.
Yeah, thank you.
Yeah, thank you.